My name is David Salvia. I am a faculty member in the Electrical Engineering Department at Penn State University, and I will serve as your instructor for this EE210 video lecture series. This video lecture series is a set of pre-recorded lectures that vary in length from about a half hour to an hour long. These lectures cover all the material in EE210. There is a note packet available in Canvas that these lectures are based on. So you want to make sure to print out this note packet so you can follow along with your notes. In addition, our lectures are loosely based on the book Electric Circuits by James Nilsson and Susan Rydell. So you would want to get a copy of that textbook as well. To be quite honest though, any introductory electric circuits textbook is probably sufficient for following along with this material. Anyway, I hope that you enjoy these lectures and learn a lot in this EE210 video lecture series. So we will begin with our first lecture.
This first packet of notes deals with a lot of basic concepts and circuit terminology that you probably saw in an introductory electromagnetics physics course such as Physics 212. You may find this material a little boring because it's a repeat of a lot of stuff you've seen already. However, it is critically important that everybody has a strong understanding of these fundamental concepts so that when we get into more complicated circuit analysis techniques, the fundamentals are not standing in the way. In today's lecture, we're going to talk about the three most fundamental concepts in electrical engineering: charge, current, and voltage. And then in the subsequent lectures, we'll talk about power and energy, and then we'll talk about the most basic circuit elements such as power supplies and resistors, and introduce Ohm's law, which is the most fundamental theorem in electrical engineering. You will want to read in the book Chapter 1, which is sort of an introductory chapter, and then Chapter 2, you want to read Section 2.1 and 2.2. Okay, we're going to start by talking about charge, which is the most basic unit in electrical engineering. Why is it so fundamentally important? Because charge and motion is what yields energy and information transfer, which is what circuits are all about. So charge and motion leads to energy and info transfer in a circuit. So you probably remember in a preliminary physics course, such as Physics 212, that all matter exhibits an electrical property known as charge, which happens when you have an excess of protons or electrons in an atom. Normally, an atom has the same number of protons or electrons. However, the electrons, which are in the outer shell of the atom, can often leave the atom, become free electrons, and that gives us an imbalance in the charge. And then related to that, you probably remember that these charged particles exhibit either a repelling or an attractive force, depending upon whether there is a positive charge or a negative charge. We'll talk about that in a minute. But before we do that, I like to talk about a mechanical analogy. One of the things we see in electrical engineering is it is very abstract because unlike mechanical systems, you can't really see what you are working with. So I like to use a lot of mechanical analogies throughout EE210 to help us visualize what is going on. So a good analogy for a charge is a mass in a mechanical system. Another good analogy would be a volume of water. We'll see throughout circuit analysis, we will use a lot of analogies that deal with water because the flow of water is sort of like the flow of electrons. We'll talk about this more soon. The notation for charge, we use the letter Q to represent charge. We typically use a capital Q when we're talking about a charge that is constant and a lowercase q, sometimes with this T argument, when we're talking about a charge that varies with time. The unit of charge is a coulomb, which is abbreviated by capital C. The definition for coulomb seems somewhat arbitrary. 1 coulomb, either plus or minus 1, is a charge needed on identical particles 1 meter apart in a vacuum to either repel or attract each other with a force of 9 times 10 to the 9 newtons. Once again, this seems extremely arbitrary, but it is the definition that we use for coulombs. So what do we mean by this definition? The distance between them, as I mentioned earlier, squared. When you have atoms that have either an excess of protons or electrons, so they exhibit electric charge, they can either be attracted or repelled from one another. And what you probably remember from physics is like charges repel each other and opposite charges attract. This is very similar to gravitational attraction between masses, except for the fact that with gravitational attraction, it's always an attractive force, whereas with charge, it could either be attracting or repelling. So imagine that you have two charged particles here, one with a charge of Q1, one with a charge of Q2. These could be positive or negative. The force between them is given by some constant K, which is 9 times 10 to the 9 Newton meter squared per Coulomb squared, times the charge of the first atom times the charge of the second atom divided by the square of the distance between the two particles. This is very similar to gravitational attraction. The only difference in gravitational force, these Q1s and Q2s are masses. Remember, I said charge was similar to mass. And of course, this coefficient out front, K, is going to be different. So a good analogy here is gravitational force. Once again, the difference is gravitational force is always attractive. Whereas this electric force can be attractive if one is positive and one is negative charged, or it could be a repelling force if, for example, both of these atoms exhibit a negative charge or a positive charge. So the question is, how many excess electrons or protons does it take to get 1 coulomb of charge? It turns out you need about 6.24 times 10 to the 18th excess electrons or protons to get 1 coulomb of charge. Once again, remembering electrons give us a negative charge and protons give us a positive charge. If you take the reciprocal of this number, you see that the charge of 1 electron or 1 proton is very, very small, plus or minus 1.6 times 10 to the minus 19 coulombs. Bottom line is 1 excess electron or 1 excess proton has a very, very, very small charge. This brings us to the next concept, current. Current important because current is nothing more than charge in motion. Basically, it is electron flow. Current is what gets things done in a circuit. And having a positive or negative charge, if the charge isn't moving anywhere, nothing happens. It is the movement of the charge in motion, the current, that causes stuff to happen. So the official definition of current, it is the net flow of charge across any cross-section in a conductor. And the key word here is the term net. At any given time, you could have electrons flowing maybe from left to right and other electrons moving from right to left. It is the net flow that dictates what the current is. And once again, this is important because this is how you get the transfer of energy or information in a circuit. So a good mechanical analogy here, couple different ones. One using mass would be a mass falling to Earth because of gravity. So for example, you might have a rock on top of a hill. The rock just sitting there doesn't do anything, but once it starts falling down the hill, it starts doing something. It has energy that can do something. Knock down a wall at the bottom of the hill, for example. Another good analogy would be water flow in a pipe. Water just sitting in a pipe doesn't do anything. Water flowing through a pipe can cause things to happen. Likewise, charges just sitting in a circuit don't do anything. Charges moving through a circuit is when things happen. For current, the notation we use is the letter I, which is a little strange. You wonder why we don't use the letter C. Turns out that we use C for capacitance much later in the semester. We sort of run out of letters, and so we use the letter I for current. And like charge, we use a capital letter when we talk about current that is constant, and we use a lowercase letter, often with the T, to indicate current that changes with time. So the unit of current is the ampere, which we use a capital A to represent. So what is the definition of an ampere? Ampere is the net motion of 1 coulomb of positive charge through a cross-section in 1 second. Couple terms in this definition are key. Once again, net. You could have electrons moving left to right and right to left. It is the net motion that really matters. The other term that's really, really important and a little confusing, it is the net motion of positive charge. The reality of it is, in the vast, vast, vast majority of circuits, it is actually the electrons that are moving, not the protons. If you think about an atom, the proton is right there in the nucleus, but the electron is in an outer layer, and the electrons are the things that can break free to cause charges in the atoms. This electron flow is what causes current to happen. However, in the early days of understanding electricity, the powers that be decided that current flow was going to be the current flow is going to be defined by the net motion of positive charge, even though it's actually negative charges that are moving. So, for this confusion, you can thank Ben Franklin. He is the one that decided the current is going to be the net flow of positive charge. There's nothing magical about calling electrons negative charges and protons positive charges. There's nothing magical about calling current the flow of positive charges. However, that was what was established centuries ago, and so that is what we are stuck with now. So if you look at this figure on the bottom here, it sort of explains this concept of current. Suppose at one point in time you have 1 coulomb of free electrons. So 6.24 times 10 to the 18 electrons, which is 1 coulomb. Suppose 1 second later, that same bunch of electrons is over on this side of this cross-sectional area. So by definition, we had a net motion of 1 coulomb of positive charges moving from left to right. We actually had negative charges moving from right to left. So it was a net motion of 1 coulomb of positive charges moving left to right. So the electron flow was from right to left, but we say that the current flow is from left to right. So we say that we have 1 ampere going from left to right, although technically we have the electrons moving from right to left. This can really confuse students early on in understanding electrical engineering, but for the most part, it's okay to think about current flowing as the movement of protons, even though technically it is electrons moving the other way. So you really don't want to get caught up on this concept, but you do want to remember that even though we always talk about current flow and think about the flow of positive charges, it's technically negative charges moving the other direction. So let's talk a little bit about current designations in a circuit. So when we talk about current, you need 2 pieces of information. You need to know the magnitude, how much current, 1 milliamp, 2 milliamps, 5 milliamps. You also need to know the direction. So you always have a magnitude and an arrow. So for example, you might say that the current is 2 milliamps, but then you also need to have a direction. Without the direction, the magnitude of the current really is meaningless. Another important point here, suppose you have a circuit, and suppose it's connected up to either a single element, maybe it's a resistor, or maybe it's a group of elements, we call that a subcircuit, and they're connected by just 2 wires. a wire here, and a wire here. If the current in this wire, let's say it's I1, turns out that the current in the other connecting wire is also I1 going the other direction. So the current flowing into, let's say, terminal A is the same as the current flowing out of terminal B if those are the only two wires connected to that part of the circuit. We're going to talk about this later, but I did want to mention it now. The other thing that's really important is we're going to be solving circuits in this course. In other words, we're going to be given a circuit where we don't know the currents or voltages ahead of time. So what we're going to have to do is come up with variables for currents and then solving some mathematical problems to determine what the current is. Suppose, for example, you have a circuit like this. I'm not going to put resistor values here, but let's say we have a bunch of resistors and a couple different power supplies, maybe a 10 volt and a 15 volt power supply. Suppose you want to determine the current through this resistor here. If you don't know it ahead of time, you give it a variable, maybe I sub x, but you also have to give it a arrow direction. You always have to have a reference direction whenever you have any current, whether it's a given current or it's a variable. You must have that. Suppose then when you solve this circuit, you solve for Ix and you determine, for example, maybe Ix was minus 4 milliamps. All that this minus means is that our initial guess of going top to bottom was wrong and the actual current flow would be 4 milliamps going up. And that is not a problem as long as you're consistent. So having a current solved for that is negative, all that means is that the arrow that we represent the current going is not really the direction of current, it's going in the other direction. You just need to be consistent and be aware of that as you go through problems. Let's spend a little bit of time looking at the charge-current relationship now. When we talk about current, there are actually two different definitions of current. There's average current, which is the net movement of charge in a given time. And there's also something called instantaneous current, which is basically a rate of change of instantaneous charge. Let me explain the difference here. So suppose you have a plot here of charge versus time. So maybe the charge looks something like that versus time. When you're talking about average current, you are concerned about two different points in time, maybe time t1 and time t2. So at t1, the charge might be that. At t2, the charge might be that. The average current then is the net change in charge, delta Q, divided by the change in time, or delta t. Another way to think about it, it is the slope connecting these two charge points. So bottom line, when you talk about average current, you always need to have two times given. So the average current between 1 second and 4 seconds. Instantaneous current, on the other hand, let's draw the same figure, or approximately the same figure. I'm not sure I'll get this squiggly line the same. You get the idea. When you talk about instantaneous current, we're talking about the current at one instant in time. And the current at that instant in time is the derivative of the charge plot. So average current is delta Q over delta T. Instantaneous current is dq dt. And obviously, the closer that these two times are in an average current, the closer it's going to be to instantaneous current. Anyway, since instantaneous current is a differential relationship between charge and current, you can reverse that and you can get that the charge is nothing more than the integral of the current. And the one thing I want to point out here is it is a definite integral. So the charge at any time t is the initial charge at time t naught plus the integral from t naught to t of the current. And I should point out here that we use a dummy variable tau within this integration to differentiate it from this t that shows up in the final equation. And we'll see this in an example in a couple pages. If we're starting at time minus infinity, whatever that means, q of t would just be the integral from minus infinity to t of I of tau d tau. Okay, let's do a couple examples now to illustrate this relationship between charge and current. So here we are given a plot of charge at a point in a circuit as a function of time. And we're asked to determine first off an expression for the instantaneous current that would deliver that charge, and then we want to find the average current between 0 and 5 seconds. So the first thing we want to do is we want to find the instantaneous current. That's going to be this answer down here. And then we want to find the average current. And notice when you talk about average current, as I mentioned before, you always need two different points in time to define average current. Okay, instantaneous current is nothing more than a derivative. So basically we need to take the derivative of this figure on top to get the instantaneous current. Well, we notice between the time -1 and 1, we have a straight line with a slope. What is the slope? Well, let's see. 6 minus 2 is 4. 4 divided by 2 is 2, so this is going to have a slope of 2. This line segment has a slope of 0. And this line segment, let's see, it goes from 6 to -4, that's a change of 10, and it takes 2 seconds to do this, so this is going to have a slope of -5. So if we wanted to plot the instantaneous current, it is nothing more than the derivative, and the derivative of a straight line is just a number. So between -1 and 1 seconds, we have 2 amps. Between 1 and 3 seconds, we have 0 amps. And between 3 and 5 seconds, we have -5 amps. At 1 second and at 3 seconds, because the derivative is undefined, because you get this sudden change here, the current is also undefined. You really don't know what the current is at that time because the current changes instantaneously. But this would be the plot of the instantaneous current. And notice once again, at points in time where you get a sudden change in the charge, you get a sudden jump in the current. So now let's look at the average current. So average current is always between 2 points in time, and the 2 points in time in this problem are 0 seconds and 5 seconds. At 0 seconds, we have 4 coulombs of charge. At 5 seconds, we have -4 coulombs of charge. So if you think about delta Q, it's going to be -8 coulombs. If you think about delta T, five seconds. So once again, if we were to connect these and find the slope is nothing more than -8/5. So we know that I average, which is delta Q over delta T, is going to be -4 minus 4 over 5 minus 0, or -8/5 of an amp. So this example illustrates the difference between instantaneous current, which is a derivative, and average current, which is just the slope of a line segment. This example goes the other way around. In this example, We're given the current as a function of time, and we're asked to find the charge. Specifically, we're asked to determine the expression for the charge transferred by the current shown above. And we're told that there's no accumulated charge at t equals 0 seconds. So now we're using the integral form of the relationship. The charge at any time t is the charge at some beginning time plus the integral from t naught to t of I of tau d tau. And we'll see here why it's important to use this dummy variable. So we're going to set t naught equal to 0 seconds. So Q of t is the accumulated charge at time 0, which was 0, plus the integral from 0 to t of I of tau d tau. So I of t is 4e to the minus t over 2. So here we write it as 4e to the minus tau over 2 d tau. We're using this dummy variable. So the integral of 4e to the minus tau over 2 is minus 2 times 4e to the minus tau over 2. So we get minus 2 times 4e to the minus tau over 2. And we want to evaluate this at the upper limit of t and the lower limit of 0. So we get minus 8 times e to the minus t over 2 minus 1. And here you see why we have to use this dummy variable. We're going to end up with the t in the final expression, so we want to use the tau here so that you can remember where you have and have not yet put the t in the substitution. Continuing then, we can rewrite this, get rid of the minus sign and rewrite this as 8 times 1 minus e to the minus t over 2. And of course the units are going to be coulombs, and this is valid for all time greater than equal to 0 seconds. If we were to plot this, we would see that it's 0 accumulated charge. At 0, you plug in e to the 0 is 1, it starts at 0, and then as time increases, this thing rises exponentially and settles at 8 coulombs. A good way to check your answer when you're going from current to charge is to take the derivative of the charge and see if you get the current. So we're not going to worry about numbers here, but just think about the shape. Here we have a slope of 0, 0, 0, 0, 0, 0, 0. Once again, a current is going to be 0. All of a sudden at time 0, we have a large positive slope. So that's going to give you a positive current. As we increase in time, notice that the slope gets smaller and smaller and smaller and ends up at 0, and so the current starts at a positive number and it stays positive, but it gets smaller and approaches 0. So once again, by looking at the charge plot and thinking about its slope, we can not necessarily prove that our answer is correct, but we sort of verified, yeah, our answer is probably correct because the current and charge has this differential relationship. So far we've talked about charge and current. It is charged particles, specifically electrons, moving in a circuit that cause the transfer of energy and information, and current is the actual movement of these electrons. But what causes these electrons to move? That is where voltage comes into play. Before we talk about voltage, though, we want to talk about electrostatic force, which is a very similar concept, which is topic that you probably learned about in Physics 212, your electromagnetics course. Electrostatic force, in basic terms, is electrical pressure. By electrical pressure, we mean is that electrostatic force is what causes current to flow. Before we talk about electrostatic force, let's talk about a similar force that you might understand a little bit easier, and that is gravitational force. Think about the Earth. The Earth is a very big body with a huge mass. it has a gravitational force associated with it. Basically, there's a gravitational field around the Earth, and any mass that is put in close proximity of the Earth is attracted to the Earth by its gravitational pull. So whether you're talking about a human, where you're basically kept on the Earth because of the gravity, or the moon, which is kept in an orbit because of the gravity, it is due to this gravitational force associated with this very, very large mass of Earth. And what happens if you have something that tries to get away from the Earth? For example, when you try to jump, you need to exert energy in order to get away from the Earth. And then what happens, the Earth just pulls you back down. So whenever you try to go against this gravitational force, you have to put energy into the system. And then when the system comes back to the Earth, it loses that energy. So the same concept can be applied to charged particles with one difference. With gravitational force, it is always an attractive force, but as we saw in the previous slides, when we talk about an electrostatic force, it can be attractive or repelling. So basically what happens is when you have a charged particle, it has an electrostatic force emanating from it. When you move another charged particle in the vicinity of that, it is either going to be pushed away from the first particle or towards it, depending upon whether they have the same charge or opposite charges. And when you try to move a charged particle against the direction of the force, you have to put energy into the charged particle, and then when the charged particle moves in the direction of the force, it loses that energy. So let's look at an example here. Suppose we have a charge, and we will arbitrarily call it a positive charge. Because it has a positive charge, it has an electrostatic field pointing out of it. So all of these lines are the electrostatic field pointing out, which means it's going to repel other positive charges. So let's say now that we take another charged particle, let's say a 1 coulomb of charge, and we place it at point A. So the charge in the center is going to be pushing that charge away. But if somehow we can move that particle at A to B, we are putting energy into that charge. We're moving it against the way it wants to move. This would be analogous to lifting a boulder up a hill. We're putting energy into the boulder. And so when this charged particle moves from A to B, it gains potential energy. And so when it moves from A to B, it gains potential energy. Anyway, voltage is what we use to measure this change in the potential energy. Specifically, we say that voltage is the change in potential energy per unit charge. So a good analogy of this would be lifting an object up a hill. You're going against the gravitational field, the gravitational force, and so you're putting energy into that object. And as you're in that higher elevation, basically that object has potential energy, so that if it rolls down that hill, it loses that potential energy and it gets converted to kinetic energy. Okay, so let's see how this relates to voltage. So as I said on the previous slide, voltage is a measure of the change or the difference in potential energy per unit charge between 2 points in a circuit. So if you look at 2 points in a circuit and measure the difference in the voltage, basically that tells you how much potential energy a charge would either gain or lose when moving from one point to the other. So let's say that we have a charge, a positive charge, moving from a higher to lower voltage. It's going in the direction that it wants to go. Charges want to go in the direction of the electrostatic force. So if a charge moves from higher to lower voltage, it goes in the direction it wants to go, which means it's going to lose energy. That's like a ball rolling down a hill. That energy that it loses is absorbed by the circuit and converted to mechanical work or dissipated as heat. So for example, it could cause a speaker to vibrate, it could cause a motor to move, it could cause a light to light. So the energy that is lost by the charge as it goes from higher to lower voltage is picked up by the circuit to do useful work. On the other hand, suppose you're moving a charge from a lower to a higher voltage. This is like rolling a ball up a hill. This requires energy to be put into the charge. That energy is absorbed by the charge in the form of potential energy to be used later on when that charge moves back down to a lower voltage. So what we see is this very important result is that naturally charges want to move from higher to lower voltage. They want to move in the direction of the electrostatic force. So a charge wants to move from higher to lower voltage, which means the current flow naturally wants to go from higher voltage to lower voltage. And what this means is that to move a charge from lower to higher voltage requires some external energy. We're going to see later on that would be a battery, for example. So once again, some analogies for voltage would be the height of an object, so the higher an object is, the more potential energy it has. That's against the way it wants to go. It wants to go to a lower height. Just likewise in a circuit, a higher voltage means that the charge has more potential energy. The charge wants to go to the lower voltage, so if it's at a higher voltage, something had to put it there. So the notation of a voltage, we use the letter V, and just like with current and charge, we use a capital to represent a voltage that is constant and a lowercase to represent a voltage that is potentially changing. The unit of voltage is a volt. And as we mentioned, voltage is energy per unit charge. So specifically, 1 volt is 1 joule change in potential energy for 1 coulomb of charge. So once again, it is energy per unit charge. It was what voltage is. When we talked about current, we saw that you had to have both a magnitude and an arrow. Likewise, when we talk about voltage designations, you need two things. You need a magnitude and you need a polarity. Voltage is even more complicated than that, however, because there are two types of voltages in a circuit, what we call relative voltage, which we'll talk about now, and what we call absolute voltage, which we'll talk about later. So relative voltage, we're talking about a voltage across an element in a circuit, or more generally, or voltage difference between any 2 points in a circuit. So when you talk about the voltage across an element or the voltage difference between any 2 points in a circuit, you need a magnitude, 5 volts, 3 volts, 2 volts, and you need a plus and minus sign to indicate which of the 2 points has the higher voltage. So for example here, if you have a circuit with point A and point B, we say that point A is V1 volts higher than point B. We have the plus associated with the A and the minus associated with the B. Just like with current, however, you don't necessarily know ahead of time which points have a higher voltage. So once again, maybe you have a circuit like this. With a couple resistors and a couple voltage sources, 10 volt and a 15 volt source. Suppose you want to find the voltage across this resistor right here. If you don't know it ahead of time, you don't know whether the point on top is a higher voltage or the point on bottom is a lower voltage. So what you do is you give it a variable, let's call it V sub x, and you arbitrarily pick a plus and a minus. The plus here and the minus here. As long as Vx is a variable, we do not know for sure whether that point up there is a higher or lower voltage than that point. You will not actually know until you solve for Vx. Suppose in this example that you solve for Vx and you get that Vx was equal to -2 volts. What this negative sign means is that your initial guess of the plus on top and the minus on bottom was wrong, and that the bottom node, the red node, is actually a higher voltage than the top node. So once again, when you're working with variables, you arbitrarily pick a plus and a minus, and then when you solve for the circuit, you might find that your plus and minus is wrong. That's not a problem at all as long as you interpret it correctly. When we talk about relative voltage, in lieu of using the plus and the minus, sometimes we use a 2 subscript notation. So for example, for this voltage up here, this V1 with the plus and minus, instead we could designate the same voltage by the designation VAB. With the 2 subscript designation, you always interpret the first point as being what you're calling the plus terminal and the second point being what you call the minus terminal. Remembering what I just said down here, that doesn't necessarily mean that point A is a higher voltage than point B. It depends upon whether this number here is positive or negative. So in addition to talking about relative voltage, the voltage between 2 points in a circuit, we also have something called an absolute voltage, which is voltage at a point in the circuit. So it turns out that in every circuit, we have a reference point that we call ground. Ground is basically what we're calling 0 volts. So if you pick a point in the circuit called 0 volts, you can now find the voltage at any other point in the circuit relative to that point. And we call that an absolute voltage designation. A good analogy to absolute voltage would be the elevation with respect to sea level. So sea level, you can sort of think of as our 0 volt point. And so the elevation at anywhere else in the world relative to that elevation of 0 gives you the elevation. So when we work with absolute voltages, we don't need the 2 subscript notation and we don't need the plus and minus polarities that we had with relative voltage, because it's always assumed that the minus is at ground and the plus is the other point. So for example, if you have a situation here, you could use a relative voltage designation, VAG, which is the voltage at point A with respect to point G. Alternately, we could just use this absolute voltage designation on the left here and say VA, which is basically assuming that we have this point G, which we're going to call ground, which is the reference voltage at which we're comparing. It turns out that there's a very simple relationship between absolute and relative voltages. Specifically, the relative voltage between any 2 points in a circuit can always be expressed as the difference between their individual absolute voltages. For example, suppose we have point A in the circuit, we have point B in a circuit, and we have another point designated as ground. So the absolute voltage at point A is VA. In other words, that is the relative voltage between point A and ground. That's given right there. Likewise, VB is the absolute voltage at point B with respect to ground. Also, you can think of it as a relative voltage between VB and ground. Anyway, the relative voltage between points VA and VB is just the difference between the 2 absolute voltages. So relative voltage between any 2 points in a circuit can always be written as the difference between 2 absolute voltages. A good analogy for the difference between relative and absolute voltages is as follows. Absolute voltage is like the altitude with respect to sea level. Relative voltage is like the height of an object. For example, let's take Mount Nittany. So it's roughly shaped like that. The elevation at the base of Mount Nittany is about 1,315 feet above sea level. The elevation at the top of Mount Nittany is about 2,000 feet above sea level. And so the actual elevation gain, the actual height of the mountain itself, is 650 feet. So The way you would get this is 650 feet is the difference between the elevation at the top minus the elevation at the bottom. Likewise, the difference in voltage between 2 points in a circuit is the difference between the voltage at one point with respect to ground minus the voltage at the other point with respect to ground. Next lecture, we will pick this up and talk about nodes and node voltages, do a couple of examples with voltages, and then we'll talk about power and energy. See you later.